People can join anytime they would like. Okay, I'm very happy to host Peter Dueben today. And when I sent him an email inviting to give a seminar, he immediately accepted, and I was very happy that he accepted our offer to give this presentation. Peter Dueben is the head of Earth System Modeling section at European Centre for Medium Range Weather Forecasts in Germany. He was in UK and now moved to Germany. How I met him is through EuroHPC projects. He's also the coordinator of MAELSTROM EuroHPC-Join Undertaking. That project aims to use optimized performance and machine learning to improve climate science and weather prediction. So I'm hoping that we will hear some of those tasks from that project and ECMWF project as well. So very glad to host you, and Peter, please, stage is yours. Thank you.
Thank you very much, and also thank you very much for the invitation. I'm going to talk about machine learning for weather and climate predictions, but whenever you feel something is more interesting, or whether you have questions or anything like this, please stop me, because I'm not 100% sure how to pitch this talk, because I assume that you guys are very much into algorithmic development and machine learning and probably also high performance computing, not so much into weather. But whenever I'm too fast or too slow, then please let me know, and I can adjust.
Yeah, Peter, the most people attending are from engineering department here at Koç University, and students are from AI Center mostly, so they will know the AI part very well, but we will be interested in hearing the weather and climate prediction and science.
That fits well to what I've prepared. Okay, so without further ado, I just jump into the slides. So before talking about machine learning, I should have one slide on who we are at the European Centre for Medium Range Weather Forecast, or also called ECMWF. So we basically we are a research institute, but we also perform operational weather predictions. So we're actually building global weather prediction models, and they're looking into the future, a couple of days into the future, and that's what we call the medium range. But we also make predictions of like seasons and months and stuff like this. And we have around 350 members of staff, and we have originally been based in Reading, but now we also the supercomputer has now moved to Bologna, and we also have now new offices in Bonn, where I'm also located now. And as we want to do operational weather predictions, we need supercomputers. So we have actually supercomputers on site that are quite big. And we also need a prediction system, obviously, and therefore we build what we call the integrated forecast system, which is one of the leading global weather prediction systems in the world. So what do we do with numerical weather predictions? So we basically have a workflow that we collect all the different observations that are coming in. Then we do a process that we call data simulation, which is basically combining observations and the forecast model from previous dates to generate initial conditions. And then we run a numerical weather forecast model into the future. And then we do some post-processing and dissemination. And to do all this, we basically need HPC power and also big data processing. So we basically have a high-performance computing problem here. And I just brought you 3 videos on the top here, which is basically showing you wind gusts at the surface for our standard system as it's running every day, basically. And what I just wanted to show you is basically the amount of detail that we have in those simulations. So each individual in simulation has 1 billion degrees of freedoms. It's very complex. It's very high resolution. So these models are kind of nothing that you would just come up with on a normal day. It's basically taking a lot of time to develop those models. And also, as you will see, there are 3 realizations of this kind of one scenario here. One of them is what we call the control forecasts, but we also have so-called perturbed forecasts. And these are basically forecasts that run with stochastic parameterization schemes, so random forcings into the mix. And this is done basically because you want to have some spreads between the possible futures that are going to be there. So if you kind of look at the difference between the different videos, you will see the predictability error that we expect for the specific simulation. So that's kind of the framework where we started from. And now the question is, like, why machine learning? And in principle, we kind of started to really look into machine learning in the sense of deep learning, basically around 2018. So we're kind of fairly late to the club, if you want. And the reason why we did this was basically because we had this exponential increase in data that we have stored in ECMWF. So we now have hundreds of petabytes of data on site. So we have a lot of data that we look into. There has also been this move towards like new machine learning hardware. So this is a slide that I've stolen from Thorsten Höfler here, where basically at some point tried to collect all the different hardware designs that are available, all the different companies that are building hardware specifically for machine learning. And we already see today that basically all the new supercomputers are kind of really customized towards deep learning applications, which basically means that even if you don't want to work with machine learning, you should think about how to use this hardware for your predictions. The next point is availability of software. So whereas we are building 1 million lines of Fortran code, big, huge models, machine learning models can run with a couple of 100 lines of Python code using the libraries that probably all of you know by now. This kind of really is speeding up progress quite a lot. And then finally, also the increase in knowledge, that we basically know much better now how to build those machine learning tools for customized applications, and that we have a huge toolbox that we can pick from. So good reasons to start with machine learning. Why would machine learning in principle help for Earth system modeling or weather and climate science? If we just focus on supervised learning for now, it's basically the simple step of learning a tool that is doing the mapping between inputs and outputs, right? There's nothing very difficult about this, about the setup in principle. But it's a tool that is very versatile, as you all know, so it can be used in various contexts. And as I told you before, we have this Earth system now that we want to model. And this Earth system is very difficult to model in principle because you have turbulent flow fields, you have very complex systems with a lot of different components like ocean, atmosphere, land surface, ice on land, ice in sea, land surface itself, and so on and so forth. And we basically can't really model all the kind of different components in all the details. So therefore, we will always have forecast errors and kind of inconsistencies there. And it's just something very difficult for conventional modeling. And on the other hand, we have this huge amount of data. So we have observations from all over the place. We have a system model data. We have reanalysis data for the last couple of decades that tell you something about the Earth system. And if you now put those 3 points together, so you have a system that can really learn this mapping procedure, input outputs, you have a system that is very complex and hard for conventional modeling, and also you have a huge amount of data available, then it's kind of quite clear that machine learning in principle can be kind of very powerful. So there are many application areas in principle how you could use this mapping procedure within this Earth system modeling framework. And also, it's kind of very good time at the moment because we also have large initiatives coming up. So there's what we call the Destination Earth project, which is a very large European Union project that is kind of realized by ECMWF, ESA, and EUMETSAT. And here we try to build what we call digital twins of the Earth. And I've shown you this plot before on the last slide, but what I haven't told you is that one half of the plot is actually showing you an observation and the other half is showing you a model simulations. And you can decide basically which one is which. So basically those simulations are so high resolution and so detailed that you can argue that they already fulfill the criteria for digital twins. And this Destination Earth project is really pushing this to very high resolution, but this also means that we're really going to very extreme amount of data output as well. So we're talking about hundreds of terabytes per forecast day, which is kind of quite crazy. So machine learning will actually help to kind of digest all this data volume. And on the other hand, given that hardware is getting more and more heterogeneous, we need to rethink the state of the art anyway. So we also are basically at the brink of what we call a digital revolution of the Earth system. And what's meant here is basically that we can't just continue writing 1 million lines of Fortran code and run on CPUs. We really have to think about how to use GPUs and other accelerators. And there we basically need to think about domain-specific languages, these kind of things, how to kind of cater for heterogeneous processing and memory architectures, how to do new methods that really can scale to hundreds of processes in parallel, and so on and so forth. And machine learning can also play a big role here in a sense that it can speed up things as emulator. It can basically help you to work with very reduced numerical precision. It can help you use very specific accelerators like tensor cores and so on and so forth. So there's a lot of, well, ground to gain here as well from machine learning. So I like to say that the first phase that we looked into with machine learning and weather and climate sciences was basically a phase from something starting from 2018 going to something like 2021. And this was really about us learning what machine learning is. So in 2018, I published my first machine learning paper, and I think many others did as well. And now we're kind of getting there in a sense that we really understand what we're doing with machine learning. And we also understand better what applications are actually useful for machine learning. So I just give you one slide where I just try to give you an overview of how machine learning is nowadays used in weather and climate sciences. So one of them is that we basically try to improve our understanding. So we actually try to, for example, fuse information from different observational data sets to kind of try to extract the most important information part from different data sets. We try to do things like unsupervised learning and try to understand causality effects in the Earth system. So what feature is impacting what other feature, and so on and so forth. We can think about visualization tools. We can think about uncertainty quantification and all these kind of things. So this is basically to improve our understanding about the Earth system. Then we have also a part which is really about speeding up simulations and green computing. So here it's really about, for example, trying to emulate a specific model component with a machine learning tool that can then run much faster and much more efficient on supercomputing facilities. It's also about porting emulators then to heterogeneous hardware using libraries like TensorFlow and so on and so forth. It's about using reduced numerical precision and sparse machine learning to really kind of make the most out of the hardware that is available. You can also think about optimization of HPC and data flow, and you can also think about methods like data compression and so on and so forth. The third group is on the improvement of models. So you can also try to basically just improve your existing system to some extent. And this could be, for example, that you learn components from observations. You kind of learn, for example, how to represent clouds just from the data that is available on clouds. Or you can also correct from model errors and model biases. And finally, you can also do things like quality control of your observations that are coming in and these kind of things, and also feature detections. And then the final part is basically that machine learning also really helps to link communities in our domain. So if you have a health data set over London, for example, and you want to understand how weather is impacting the health conditions in London, you can just use machine learning to do the mapping between weather data, for example, and the health data set. And this is typically very difficult because you wouldn't know how to basically combine the two worlds. But if you have machine learning, it can just be trained and learned. So this kind of machine learning is really helping to also bridge communities to the end user, basically starting from weather forecasts, going to, for example, energy production, transport, pollution, extremes, and all these kind of things. And it's very powerful there as well. So there are good reasons to look into machine learning for weather and climate, and many people do. The things that we learned over this kind of first phase, one of them is to basically to think about what we call the physics-informed machine learning. And I'm sure a lot of people in the room here are actually also doing one way or the other physics-informed machine learning. It's also sometimes called trustworthy AI or explainable AI. But in principle, the idea is the same for each of them, that you basically try to learn a better machine learning tool based on a physical knowledge that you kind of combine with this kind of black box of machine learning. And there are a lot of different ways how to do this. So you can formulate the machine learning problem in a way that makes it physical. You can change the architecture of neural networks that we're working with. You can close budgets. You can basically incorporate physical constraints and loss functions. You can solve differential equations straight away with neural networks, and so on and so forth. And there are also ways how you can basically make sure that there is kind of physical consistency in the solution that you get by, for example, looking into a specific weather scenario or looking into energy budgets and so on and so forth. So that's kind of a great topic if you nowadays want to write research grants, basically. But it's also that it comes with some uncertainty in a sense that a lot of those, there's an elephant in the room here, because basically we still don't really know exactly what physics-informed machine learning is, because there are a lot of different approaches that are not really consistent with each other. There's also not a holistic approach that if you would basically follow this one approach, you would get a physically consistent answer, but they're more like different approaches trying to kind of patch different inconsistencies in the machine learning solution. And finally, there's also often a trade-off between understanding and scalability, which is also sometimes an issue. So often just a scalable problem with a huge amount of data is better suited for, or more physical, basically, than a physically consistent problem that can't really take all the data in because it is working with a lot of constraints. Another thing that we need to learn is basically also this kind of scale interactions and the representation of our of the bridges between different scales in the system. So in the weather and climate model, you basically bridge scales between the micro scale, where you have something like microphysics and turbulence, all the way to the planetary scale, where you have features like ENSO or El Niño and these kind of very large scale global patterns. And if you want to do good predictions, you basically need to represent all those interactions between the scales. And in principle, machine learning can do this. So if you think about, for example, an encoding-decoding network, you can basically think about having high resolution at the input and at the output, but encoding something like a coarse resolution scale within the latent space, within the encoding decoding network. So in principle, you can think about actually representing those scale interactions well. And there are a lot of different ways how to do this. And actually also a couple of success stories. So this is, for example, from a paper where we used activation layers to kind of to look into the time dimension of precipitation data sets. And we basically went from 6-hourly data to daily data, to weekly data, and then back again to daily data, basically crossing those scales in this encoding decoding way, but also using activation layers from natural language processing to basically encode this kind of interactions in the most optimal way. And we get better results using those methods. So the good news is a lot of people are using kind of machine learning to look into scale interactions. But again, the bad news and the elephant in the room to some extent is that we're still far away from a theory. So a lot of this is still trial and error, and we're basically still not very confident in why we do things. We can basically just try out things and they work or don't. I'm now going to switch to kind of 3 scientific examples that I would just want to give you a better idea of what kind of applications we're actually looking into. And one of them is what we call downscaling, which is probably what you would call upscaling in the machine learning world. So what we do here is we take model output data. So for example, precipitation fields over the UK, and the model output is at 10-kilometer resolution, like this one. But we have observations available at much higher resolution. So we have precipitation observations over the UK at 1-kilometer resolution. And the question is now, can we actually reproduce some of those small scale features in very high resolution observations just using the input of the coarse resolution model simulations, because that would help us basically to make more localized predictions into the future. And you can learn this mapping, no problem. Why not? That's easy to do. But if you do this, you basically don't learn uncertainties. So the question is, how can you actually also learn the uncertainty that you have within the mapping procedure? And it turns out that methods like GANs, generative adversarial networks, are actually very well suited to represent this uncertainty. How is a GAN working? You basically take a very large data set with real samples, and then you try to build a generator that is kind of generating samples that could come from this real sample distributions using some noise as input. And when you do this, you basically get something that can do this mapping from the coarse resolution to the fine resolution. But then you also train a discriminator that is trying to identify whether a sample is coming from the real sample part or from the generator part. And you basically have now 2 deep learning solutions that are working against each other and trying to kind of optimize themselves. And if you do this, you basically can get a mapping procedure from here to the middle down in the bottom, and you basically get different realizations when using different noise terms. And you see that they can be quite different, but all of them look very realistic in terms of like how this precipitation field could actually look like. And we get quite good results in this uncertainty representation as well. So that's also very interesting for us. Another example is the use of transformer networks for ensemble post-processing. So I told you before that we don't run only one forecast into the future, but we run 50 ensemble members. So all of those ensemble members are kind of perturbed slightly. And you do this to basically try to get the right spread of uncertainty. So you don't want to know exactly whether it's going to rain in Istanbul in 5 days from now, but you also want to know the probability that it's going to rain more than 2 millimeters, for example, right? You want to basically get probabilities with it. And if you have 50 predictions, you basically can get a probability distributions, but often this distribution doesn't really cover the real uncertainty range. So you want to post-process this to optimize basically for the optimal predictions. And it turns out that transformer networks that are coming from language processing are actually very well suited for this task. So transformer networks basically help language models to kind of combine the importance of different words in a sentence to kind of different words in the sentence. For example, in the sentence here, the animal didn't cross the street because it was too tired, could basically refer to all those words on the left, but it's kind of quite sure the transformer would actually identify that it's coming from the animal. And it could also do this for looking at a very long sentence and kind of quite a lot of space in between. So that's the magic of transformers. And we tried whether you can actually also use transformer tools in the ensemble dimension. So you would have different ways of how you can use transformers in 4-dimensional data with 3-dimensional space and 1 in time, plus 1 ensemble dimension. And we try to use it actually in the ensemble dimension. And we actually get quite good results. So this is from a collaboration together with Microsoft, where we used UNet structures. So you basically put high resolution fields in on the left, and you get high resolution fields out on the right, but we have this kind of unit structure in here. And we use transformer in the ensemble dimension to kind of adjust the different ensemble members. And by doing this, we get better results than before. So on the right, you see what we call the CRPS, which is an ensemble score. The lower, the better. And you will see that the raw ensemble is a black line. If you do like some kind of quite sophisticated but still conventional post-processing, you get the blue line. And if you use those transformer networks, you get a kind of a much lower reduced line that can give you something like a half a day lead time in the forecast quality. And the third fine example is about the emulation. So I told you before that it's not always just about improving things and building new tools. It's also about speeding up forecast simulations on existing hardware. And what we do here is that we basically run a model, and then we take a specific part, in this case, the radiation scheme, which is basically looking into how the sun is interacting with the vertical grid column and clouds in the system. And we basically just store input and output parts of this very expensive radiation scheme, and then we try to emulate it with a neural network. And we can do this with the conventional tool that we're working with, but we can also do this with a very expensive tool that we typically can't use because it's too expensive. So we basically take a very kind of expensive hybrid of this radiation model and try to learn it with deep learning. And what you get is basically quite good results. So this is how the radiation should look like. On the left, if you kind of take a cross-section from the South Pole to the North Pole, and you basically look at the different cloud fields and how they interact with the radiation scheme here, you see a certain pattern, and you also see more or less the same pattern on the right side. However, the pattern on the right side is basically a fraction of a percentage from the cost from the pattern on the left side. And if you plug this back into a weather forecast system, you actually get quite good results. So the idea here really is to kind of replace very expensive components by emulators, and this also seems to work out quite well. And that's also one of the applications that we look into in MAELSTROM. So that was the first phase of machine learning. So what is the second phase? Basically starting in 2022, and it's kind of now all the way going to what's going to stick around for a while for us. And this is really that so far we were talking a lot about the amazing parts how machine learning can interact with our systems, but we actually don't really have a lot of success stories. So if we kind of look at all the great success stories that we have had so far for operational predictions, there is again an elephant in the room. And the elephant is basically that we don't really have a lot of tools that are working yet in operations. So we still haven't done this big step to actually push our new developments now that we do on a science level into the operational framework. And this has to change, and there's no question that this really has to change if we want to make the best out of, well, if you want to make the best out of machine learning and operational for better weather and climate predictions soon. So the most promising candidates for machine learning applications that we have at ECMWF are basically the ensemble and post-processing, and there are a couple of other things like emulation and so on and so forth. And we are close. It's getting there, but we still need to kind of do this very big steps still. It's actually more complicated than one may think to really come up with a very good operational use of those models. And one reason is basically because the operational part is kind of quite static, and it's often developments for operations take a long time, but they still need to kind of be updated quite quickly. And I bring another science example here where we try to basically predict the model error that we have in our systems. So the idea is that you have data simulation now, so you have the model trajectory very close to the observations, and it's so close that within 12 hours you can actually diagnose the error that you make within your model. And once you've done this, you can actually learn this model error. And once you have learned the model error, you could potentially correct for this model error in your forecast simulations. So that's a great idea. We have tested this together in a collaboration with NVIDIA. So how far did we go? On the left, you see basically the error that we have diagnosed within our data simulation framework. And on the right, you see the neural network predictions if you just give it the state of the atmosphere at a specific time. And you see that the features are looking very similar. They're actually surprisingly similar. It's really working surprisingly well, and we're very pleased with the results here. So what about operational implementation of those results? So the downside now is that for those plots here, we used 12 years of basically analysis data. So 12 years of data simulations to generate the training data. And if we now upgrade our model, our error patterns will change. This basically means that you would need an updated version of the error correction. And for this, you would only have something like half a year of training data. So the error patterns will change now from the top to the bottom line, but you have a much, much shorter training data set. And you now use transfer learning, basically starting from this solution up here to kind of get to a new solution, but you will still see that the transfer learning didn't work out very well, in a sense that the patterns look still very much the same as they look on the top. And it's still getting benefit, giving benefit to the system, but they're really difficult questions how you integrate those schemes into operational predictions. The second part that we do in this phase 2 is basically also that we really need to come together as a community and develop like really kind of tools that are for the best use and kind of push the community as fast as possible forward. And one of them is that we want to develop what we call benchmark data sets. And those of you doing machine learning, they will know what benchmark data sets is in principle. So the idea is that you basically have a machine learning problem and you define a clear problem statement. You also basically put data together and make it available online. You have Python and Jupyter notebooks that can read in the data and kind of make some sort of machine learning reference machine learning solutions. And then you also have diagnostics and evaluation metrics that people can look into. And finally, you can also state computational benchmarks in terms of like how costly was actually this exercise. And if you do this as a domain scientist, then a lot of machine learning scientists or HPC scientists can actually grab this data set and apply the benchmark and really learn on the specific tasks that is important for the domain of weather and climate without being an expert. So that you basically separate the concerns to some extent, and this really helps you to get more people engaged with your own domain-specific problem. And it will also help if you want to optimize a specific high-performance computing configurations, for example, for a machine learning problem, because then you can also compare different networks, for example, on different hardware and how they relate to each other in terms of the cost for the computing, but also in terms of the quality of the results. And this is something that we should do more. So we kind of got together with a couple of people from weather and climate domain, and we kind of came up with lists where we would need those benchmarks. And the list is very long. So we have basically a need for benchmark data sets in all those different boxes here. You can also state that this is kind of a list of the challenges that we have right now in weather and climate science. But there's definitely more that we should do into this direction. And this is kind of also the core of the MAELSTROM project that Dueben is kind of has already mentioned that I'm coordinating. So in MAELSTROM, we basically put together 7 different groups from the weather centers, but also from hardware developers and also from machine learning scientists, basically. And we try to build what we call a co-design cycle. So we're actually going to develop 6 weather and climate applications that are very relevant across this workflow of weather and climate sciences. And then we're basically going to develop benchmark data sets for those applications. And we're also going to develop new machine learning solutions. And once we've done this, we're also going to develop workflow tools that allow like for proper software benchmarking of those systems. And we basically develop workflow tools that can then be used across the community of weather and climate sciences to build machine learning tools. And then finally, we also really develop bespoke system designs for hardware designs, basically to kind of make the most for the specific application and the specific software framework, kind of exploring the space of hardware capabilities there. And the idea is then that we will in the end also come up with compute system designs. So that's the basic idea about MAELSTROM. And if you want to get involved, we already have those benchmark data sets published. We also have hardware benchmarks already online. So you can basically go to our webpage and download those benchmark data sets and get in and get your hands dirty straight away, more or less, with relevant machine learning applications for weather and climate. Okay, so that was kind of the two parts of the talk, and there's one part missing, which is the phase X. So as you all know, nowadays people are talking about the big push for machine learning to replace everything, right? So what will machine learning basically do to kind of language process, language understanding, and these kind of things, and how will the entire domain change? And the question here is basically whether machine learning will also replace full weather and climate models in the future. So that's what I call phase X. And obviously, you all know the examples of ChatGPT kind of being amazing in what they do. And also kind of things like examples where you have machine learning tools winning art competitions and so on and so forth. You really have to ask the questions like how many domains are going to be replaced in the future by machine learning. So the question is weather and climate going to be one of those in the future? And it's actually not a stupid question, because there are people actively working towards this to some extent. So this is a snapshot that I've taken from Jensen's GTC, Jensen Huang, who's the CEO of NVIDIA GTC conference. And I think he's actually giving another keynote conference talk today. So if you want to get an update, have a look there. And Jensen was basically talking about the different revolutions that we had in high performance computing, going from single processor speed up to accelerated computing to basically scale up and out into hundred thousands of processors. And then machine learning is basically going to be the new revolution of high performance computing. And it's given an example of a weather and climate model where NVIDIA basically built what they call ForecastNet, which is nothing else than a medium range weather prediction system for the global scale. And they're kind of building also this kind of S2 initiative now with a big supercomputer and so on and so forth. So they are investing quite a lot of resources, if you want, to kind of build those very large weather and climate systems. So can we replace Earth system models by deep learning? The answer to this question just depends a little bit on what you want to do. So one of the things that people want to do is what we call nowcasting. And in nowcasting, look a couple of hours into the future. And by doing this, you basically are very much observation-based, and you're very much time constraints. So you really have only a couple of minutes to come up with a solution based on observation data sets. And this is actually a very nice application for machine learning, because physical constraint doesn't really count for a couple of hours. And also, you basically just learn straight away from your data the signal. So you don't really need a lot of physical consistency there. And there's a paper by Google, for example, showing that for precipitation forecasts over Seattle, as shown in this one here, you actually get very good results. And it's quite likely that machine learning will really replace the existing configurations there. Another example is if you look into very long-term timescales. If you look into, if you want to predict the probability for rain in Istanbul, for example, in 3 months from now, it's not impossible in the sense that you can actually get a correlation of the signal of the forecast and the real world. But it's going to be very small, so it's going to be very statistical. It's a very statistical challenge. So you wouldn't want to predict whether it's going to rain in the 4th July at 8 a.m. in the morning, but you would rather want to predict whether it's more likely to rain than usual. And for this, machine learning tools are also very much credible and very useful because it's a statistical task, and we have data there as well. The other thing is climate. So if you want to make a climate predictions, our machine learning models have a huge problem, which is that they can't really extrapolate into the future. So they just don't have the training data to actually know what's going to happen in 50 years from now in terms of climate change and these kind of things. So we basically have not really a good handle to kind of build very good prediction systems. But for us at ECMWF, the big question is what's happening at the medium range, like a couple of days into the future, if you look at global weather predictions. And there has been recently a paper coming out by GraphCast, which is basically a team from Google and DeepMind, where they kind of they built a very capable prediction systems. So if you don't do ensemble predictions, but rather deterministic predictions, they're basically beating our deterministic forecasts in a lot of quantities. So on the left, you see what we call a scorecard. You don't need to look into all the details. There are different fields and the y-axis, like geopotential, temperature, velocity, and so on and so forth, and different vertical heights in the system. And whenever this card is blue, it basically means that Google is better than our predictions. And it's blue all over the place, right? Which basically means that the Google prediction is quite good. It still doesn't mean that the ensemble predictions, which are more important for medium range, are better, but they will probably get there. And the question is now, what does it actually mean for the domain that we're working in? And how do these models actually work? So one thing that should be said is that they are trained towards a very small root mean square error. And this basically means that they are avoiding double penalty by, for example, predicting a front, but in the wrong location and these kind of things. And this basically means that they're smearing out for longer lead times. So if you have a prediction like here, you have the truth on the left. It's a global field, basically. The forecast goes from top to bottom, and you will see on the truth is the gradients are always similarly sharp, but in the machine learning forecast, the gradients will smear out. So the forecast is actually not really doing a forecast model in the sense that it's kind of representing the propagation of the 3-dimensional atmosphere, but it's rather an interpolator towards this specific forecast loss function. And also the best results you get with those machine learning tools using extremely long timescale steps. So you're basically talking about time steps of something like 6 hours or 1 day or something like this in comparison to a conventional model that would work with something like 600 seconds. And you can do this because you don't need to care about CFL conditions and these kind of things. So numerical constraints don't really bother you. But this also will basically mean that you would also smear out probably the solutions. And we don't really know what we do there in terms of implicit, explicit. The models don't really solve physical equations. They learn to please the scores. And I'm not saying that's a bad thing, right? So if you want to have a weather prediction, you want to have a very low root mean square error for a 3-day prediction, for example. So it's not, I'm not saying that this makes them unuseful. On the contrary, they're actually kind of really, really good. But it's still going to be interesting that for some applications, probably the conventional models will still be better if you, for example, look into extreme precipitation fields and consistent spatial areas, for example, that are very important there. The conventional model will probably still beat this, but if you just want to know the most likely temperature in Istanbul in 3 days, then those machine learning models will be very, very competitive, if not better. So there are a lot of questions still that need to be answered, like how can they extrapolate, how can uncertainty be represented, and so on and so forth. But this field is progressing at an enormous speed, so we will learn much more in the future about this. So what will the forecast system of the future then look like? And I kind of have fairly strong feelings here in a sense that I'm convinced it's not going to be either or. It's not going to be conventional model or machine learning. I think it's going to be a world where you have basically 3 tiers. One of them is a conventional modeling world, one of them is a hybrid modeling world, and one of them is a pure machine learning world. And I know that's a busy slide, but it's probably important still to kind of show you the differences between the different worlds. So in the conventional model world, we basically have math services who are playing the biggest role. In the pure machine learning models, it's really technology companies investing at the moment, like Google, DeepMind, NVIDIA, Microsoft, Huawei. They're all building their own weather models. And math services will catch up at some point, but at the moment, it's really driven by the technology companies. The development cycles of conventional models are something like decades, and you typically need something like 10 to 100 developers to actually make something useful in this domain. Whereas for the machine learning model, you're basically talking about years of development cycles and teams of something like 1 to 10 people. So it's kind of much more dynamic there. The tools are different. So we're working with Fortrans and DSLs in the conventional side and Python and TensorFlow in the machine learning sides. Also the hardware, I mean, we just learn how to use GPUs basically, whereas machine learning tools can use all sorts of accelerators and very low precision arithmetic and these kind of things. So they have a very big advantage here. We basically tackle data handling infrastructure questions on the conventional sides, while we really basically need just to generate training data sets, but then we also need to learn how to train efficiently from those training data sets that can be hundreds of terabytes in the future, I'm sure. So that's also like a new task, basically, that is slightly different to what we do in conventional modeling. We typically run those models really on the largest machines in the world, so we kind of to run on machines like Summit, Fugaku. We now basically port to Lumi and so on and so forth. So we're basically going towards an exascale problem, whereas here we're still talking about small applications, but rapidly growing. For the training, we're probably talking about petascale soon, whereas for the inference, we still do it on single nodes. The conventional models are really unbeatable in terms of reliability and physical consistency. And this is not going to change soon, but they're really bad in time to solution in comparison, whereas the machine learning models are basically unbeatable in scores, and also time to solution. But it's unclear how they will perform in data simulation, whereas here the hybrid models will actually be unbeatable, where you combine and make the best of both worlds with machine learning and conventional modeling combined. I skipped the next one, but for climate simulations, really, I don't think that we will get anywhere close to what we can do and with a machine learning solution than what you can do with the conventional models. And also, it's fair to say that the pure machine learning models really also require high quality data sets, and they're typically coming actually from the conventional models. So at the moment, the machine learning models are still rely on the data sets from the conventional models, and this is also not going to change, I'm pretty sure. Okay, I'm going to go to the next slides now. Just one heads up, if you're getting interested in the field of machine learning for weather and climate, but you want to learn more, we have something that we call a MOOC, which is a massive open online course. So you can basically just go to this webpage here and register, and you will see a lot of training material kind of giving you an introduction to weather and climate modeling principle, all the way to kind of very specific science applications with machine learning. Over the coursework of a couple of weeks and months, basically, you will learn more and more about this. It was a huge success. So we have, I think, more than 7,000 registrations so far. So please join us if you want to learn more about this. And also, I just wanted to phrase that we have a lot of open positions at the moment, also in the context of machine learning at ECMWF. And there we're really searching for machine learning experts and high performance computing experts. So maybe someone in this room is also interested to look at this a bit more. And the final point I want to make is that it's also not just about the prediction itself. It's also about the workflow, how we work with in our daily lives. And if you basically imagine that the domain scientists could in the future have all the different data sets next to each other, whether it's observations or model or reanalysis or whatnot, and they would have tools to basically map between the different observations data sets in a very efficient way at scale, and also have a physical interpretation of the mapping procedures, they could learn something there. They could also do uncertainty quantifications if you compare one data set to the other, and so on and so forth. And if all of this would be basically efficient, scalable in a Python, Jupyter, Julia world, this would be a tool that it would be really, really pushing the entire community forward. So machine learning can really also be seen as an enabler, basically, for the community in science in the future. Okay, that's all I wanted to say, and thank you for your attention.
Thank you very much. Thank you, Peter. That was a nice talk. Okay, so we can get some questions from the audience. Some of the... Oh, okay. There are some questions in the chat. I didn't see those. So some, like, I think you can speak up, or should I read your questions? Okay, I don't know if this KB, because you abbreviated your name.
It's making echo because our guest in here now, Jeremiah, right?
Okay, do you want me to read the question? Is that what you're saying?
Thanks, Luna.
Okay, thank you. Wow, there are 6 questions. So, okay, is it known that because of global warming, frequency and severity of rare events increase? Cyclones get deeper, long-term drought, floods, heavy snowfalls, which I assume causes to forecast weather events harder because of not having those cases in the training data. What kind of techniques do you apply for forecasting these phenomena? Besides of this, are you in contact with the governments to prevent these rare weather events?
So that's an excellent question. It's kind of related to the points that I made about climate predictions, right? If you can only learn what's in your training data set, and if the frequency and the kind of severity of the events is changing over time, you're not quite sure whether you actually will be able to predict the event as a full scale, for example. And this is an issue for all machine learning parts. The pure machine learning models still performing quite well, in the sense that even if you look into tropical cyclones, for example, they are actually performing quite well. Whether they also will perform well for other extreme events will need to be shown. For example, precipitation events, it's quite likely that they will not be as good there. But it's something that we still need to understand and diagnose, basically. The good thing in our community is that we have a lot of cases to look into. So we have the extreme events of last year, for example, that we can evaluate for how the machine learning models performed there. So we will get a good feeling of what the models can and can't do. But it's a very good question. Whether we work together with the governments indirectly, because we are basically an intergovernmental organization, but we are hosted by the member states. So for example, the German Weather Service, for example, would get information from us, and they would then talk to the local governments. And that's the same for all the member states that we have. So we kind of have an indirect way of basically talking to the governments, and also our forecasts are basically also used. If there's a very severe tropical cyclone approaching the US, for example, they would also look into our forecast and then kind of also inform policymakers. So it's kind of a bit of an indirect effect there.
Okay. Before asking Kerem's next question, is there any other question from the audience? Then Gürkan, you have a question? Yes.
Hello, thank you for the presentation. So my question will be, you said that for conventional methods, they are actually good at simulating climate events or like long-term events. So if you can have this kind of simulations, why can't we produce data for machine learning models?
Yeah, again, an excellent question. Our climate models are good. They're as good as they can be. They have their issues. They're not perfect, but they give you a reasonable prediction into the future, I would say, and they're also getting better each year. But then your question is perfectly valid in the sense that, like, if you can do a climate prediction, you can just use the climate model data to learn from it, and that's what people do. But then the question is, I mean, the huge edge that you get in weather forecasting, that you basically can produce something that is taking half of our supercomputers for an hour to kind of make 15-day predictions you can do on a single GPU with a machine learning tool. This edge is not the same in climate modeling, right? You would still need to develop a climate model that you cannot trust, and then you would kind of need to get training data and learn from the training data and these kind of things. So it's a bit less obvious how you would kind of really make the huge edge if you want, but it is possible. I agree. Yeah.
Thanks.
Okay. Do we have any other questions from the audience? I'll move to Kerem's question.
Yeah, I think the second question is about in our data archive, you can basically get what we call the reanalysis scheme. And in the reanalysis, you basically have like decades worth of data, how the atmosphere looked like at a specific point in time. And the question is how we can actually know the pressure fields in the 70s, for example, because we don't really have a lot of observations there. But we have some observations, and they're coming from various different sources. And we basically, what we do there is we perform data simulation over time. And we just take what we would use as initial conditions for the forecast. So it's basically combining a very good forecast model with all the information from the observations, and then you can fill the gaps. So if you don't know the temperature at 850 hectopascals somewhere, you can basically fill it up with information from the forecast model. And our forecast on the data simulation system is quite good in the sense that we can, even if we don't have like a very dense network of observations, we can still generate conditions that are very much realistic. So this is kind of you basically use the forecast model to fill the gaps where you don't have observations. I think that's probably the answer to the question.
Do we have other questions from the audience? I was going to ask a question about these technology companies that you mentioned, that they are investing also in weather forecast and climate models. So what are their incentives? Are they planning to make profit, or they are just using it as a use case? Do you have any idea, or?
The answer is I don't know. I mean, a lot of the technology companies are basically also doing it for the sake of showing that machine learning is useful, and also for the sake of showing that high performance computing can do things that are amazing, right? So I think it's not the number one incentive to really build a global weather prediction system and do forecasts and beat our scores, for example. But it's very difficult to really understand what the companies want to do. I think it's also fair. I think they also sometimes just want to kind of look into another really challenging machine learning application, because then if they learn, for example, how to do scale interactions in weather and climate, then this information can also help them to build the next ChatGPT model or whatnot, right? So basically looking around will help those technology companies as well to kind of build, to get more ideas and interesting applications. And also, I mean, sometimes publicity is probably also important. I mean, they're heading for kind of very highly cited papers as well and stuff like this. But it is a good question, because in principle, the amount of money that is in the weather and climate domain is not very large if you are a huge technology company, right? I would be surprised if they could really make a business model out of this. And also in a sense that even if they would beat our forecasts by a little bit, by a small margin, our forecasts are also not that expensive that it would really make a case of basically building their own development tool. So the short answer is I don't really know. But they probably have more than. I don't think they're interested in building just a tool to sell weather forecasts, and I don't think that's the case.
Okay.
It's also questionable how long this will continue. So how long will actually Google and DeepMind be interested in weather forecasts? Maybe they will drop it in 2 years. I don't know.
Okay. There are some questions in the chat if you would like to answer any of them. Or we can get questions from the audience. There are more.
So the third question is it's very specific. So I assume that Kerem is actually looking into weather applications at the moment. So about the forecast frequency, we have basically 2 forecasts per day that we're running our forecast systems at 6 o'clock and at 18 o'clock basically, and we put them online. I'm not quite sure about the specifics here about why the forecasts were not available. I don't know, but in principle we have basically twice a day the forecast run.
Maybe the 5th question you can answer. Are you also include forecasting weather events of planets in solar? Do you have any cooperation with NASA or ESA? I don't know.
Well, we have a lot of collaboration with NASA and ESA, but more like at Earth system, because we get the observations from them. So they build satellites that are orbiting the Earth, and then we get a lot of weather observations from them. And we use this data is really, really essential for our predictions. So we kind of also a use case for them. So if ESA is building a satellite for €1 billion or something like this, then it's quite good for them if someone is making something useful out of the information that's coming from the satellite. And we are basically doing this with weather predictions. So we have very strong links to them. In terms of space weather, if that's a question about like planet events in the solar system and so on and so forth, we don't do much there. I just gave a talk a couple of weeks ago at a conference about exactly this, basically. But the problem there is that you don't have a lot of data that you can learn from. So again, you would probably build the model first, and then you would probably learn from the model data. And we don't have the model at the moment in many cases. So I think it's still it's much less defined than the Earth system.
Mm-hmm. Okay, so you mentioned benchmarks that are available from the MAELSTROM project. Can you tell a little bit more about the nature of these benchmarks? Do you have the data associated with the benchmarks? How representative of those benchmarks, the real applications? Because I imagine the weather forecast code is kind of a huge code that, an outsider is not probably easy for them to grasp. So how big are the benchmarks, and is it easy to use them? Can you comment on that?
Yeah, so we picked 6 applications that are trying to kind of represent the breadth of the different application areas within weather and climate. So we have 6 applications where we basically think that they cover the space of what people typically do with machine learning and weather and climate. And those applications are kind of formulated as a benchmark data set that's online. So you can basically go to the webpage in a GitHub repository. You will get a Jupyter notebook that you can download. You can basically just start the Jupyter notebook. It will download the data for you, and then it will also kind of run a specific machine learning applications and train it for you. And then you will also get information about how quick this typically is done if you use, for example, I don't know, a V100 GPU or something like this, or the CPU systems and so on and so forth from our hardware benchmark. So it should be fairly easy to be used. It also will come in tiers, so you can basically get a smaller project, or you can also get a larger data set if you wanted to. The one thing that we don't cover yet, and we will change this in the future, is that we don't cover this global weather prediction problem. And then the simple reason is because when we wrote the proposal, I think it was actually 2018 or 2019, this kind of domain was kind of still very much in the infancy, so it wasn't very likely that it would have such a big impact as it has right now. So that's the one application that we don't cover too much. But otherwise, you should be able to basically go to the webpage, download the Git repo, and then straight away jump into the Jupyter notebook and click through yourself and click through the downloading of the data and also the evaluation of the machine learning task. And if that's not the case, please let me know, because then we would need to improve this.
Okay. So one last question about MOOC. I think it's a very nice, project you guys are doing. So you said it will start in September. Maybe I will ask you to share some information about it that I will also send to our undergrads and grad students if they want to enroll. So how long is the training or the course? Is it 8 weeks or a couple of weeks? Can you?
Yeah.
Or 1 day? So I didn't get that part.
Yeah, no worries. It actually already has started. So it was 9/1/2023, which means it started. It was not the American way of writing a date.
Oh,
it was basically saying.
So, but you will probably repeat it then.
Well, the idea is basically it's running at the moment. It started in January and it's running at the moment. And each week we will basically publish new training material that will have a couple of hours of basically participant time. So for each week there would be a couple of hours of material. And it started in January and it's still ongoing until mid-April.
Mm-hmm.
However, the material will stay there. So in principle, it's anyway designed in a way that the participant can do it at their own pace. Mm-hmm. And the material is there to stay. So even if you in 2 years decide that you want to learn more about weather and climate, you should still be able to basically go there and go through this at your own pace.
Mm-hmm. Okay.
Yeah.
Okay. Thank you very much. Our time is almost up. And I guess, do we have any other last question to Peter? Otherwise, we will end this seminar. Yes, no, thank you, Peter. I hope to see you in person.
Yes, I'm sure we will soon.
Okay. Bye-bye.
Thank you. Bye-bye.